In this video, we are going to talk about the isobaric process, and we are going to answer review problems for this particular topic. So an isobaric process is a thermodynamic process in which the pressure remains constant. So the notation would be the change in pressure would be equal to 0. So if we will draw our PV plane, pressure volume plane, then let's say that this is point 1. So if pressure is constant, then therefore you would have a straight horizontal line until point 2. So this represents, the first point would represent in the horizontal axis V1, and this would represent here V sub 2 for point 2. And the area under this curve is actually equal to the integral of PdV, and you will learn later on that we'll discuss later on that the integral of PdV, as I've also said in the isometric process video, that your PdV is equal to your non-flow work. Okay, so imagine the isobaric process being let's take into consideration this example of being let's say this is a cylinder and you have a piston. Okay, you have a piston that goes up and down. Okay, just like in a car's cylinder, so you have a piston which would transmit the work. So you have here your working substance, and if you add heat to your working substance, then therefore it would produce work, pushing the piston up. That would cause a change in internal energy, and also that would cause non-flow work. Okay, so that is just a brief background. All formulas will be discussed during the example problems. So let's answer problem number 1. So we have 3 pounds of perfect gas with R is equal to 38.8 foot-pound force per pound mass Rankine, and K is equal to 1.667. Have 300 BTU of heat added during a reversible non-flow constant pressure change of state. So this term right here, constant pressure change of state, it means that this problem falls under the isobaric process. The initial temperature is 100 degrees Fahrenheit. Determine letter A, the final temperature, the change in enthalpy, the work, and the change of entropy. So we have mass is equal to 3 pounds. We also have R is equal to 38 foot-pound force per pound mass Rankine. Then you have K is equal to 1.667, and then Q, the term here is added, so therefore Q is positive 300 BTU. And then we have T1 is equal to 100 degrees Fahrenheit, so we add 460 for it to become absolute, so we'll have 560 Rankine. Now, first determine the final temperature. So final temperature is T sub 2. Okay, so where are we going to get the formula to solve for T sub 2? Look here that we are given the heat. Okay, and the heat for an isobaric process is equal to mCp times T2 minus T1. So it's always this formula, mc delta T, no? Change in temperature. Now your C changes to C sub P, the constant pressure for specific heat, or the specific heat at constant pressure, I should say, no? C sub P. In our isometric discussion, this was M sub V because that is an isometric process. So we can solve here for T sub 2, and T sub 2 would simply be equal to Q plus mCp T sub 1 over mCp. Okay, so we have our heat, we have our initial temperature. What we don't have here, we also have our mass. What we don't have here is our C sub P. So for C sub P, we should apply the formula Kr over K minus 1, since we are given the ratio of specific heat and also the specific gas constant. So let's go ahead and solve that first. We have 1.667 times 38, then divided by 0.667. Okay, so the unit here would be the unit of your R. So let's get our calculator. We have 1.667 times 38 and then divided by 0.667. So the answer is 94.97. This is in pound force feet per pound mass Rankine. But as you can see here, your Q is in BTU. Okay? So this should also be in BTU. So we know what we need to do there. We simply have to divide 778. So our C sub P is 0.122. C sub P is 0.122. This will now be in BTU per pound mass Rankine. Okay, so let's answer T sub 2. Let's input our given here. So we have Q as 300 BTU plus mass. Mass is equal to 3 pounds. Just want to make sure. And then Cp is 0.122. So this is BTU per pound mass Rankine. And then T sub 1 is 560 Rankine. Then we divide that by our mass again, 3 pounds. And then C sub P is 0.122 BTU per pound mass Rankine. Okay? So let's examine the units that can be cancelled. We have here pound mass as cancel unit, and then Rankine here we have pound mass. So the unit for the numerator is actually BTU, and then for the denominator it is BTU per Rankine. So BTU cancels out and the final unit would be in Rankine. So let's get our calculator again to solve for our T sub 2. So we have 300 plus, we have 3 times 0.122 times 560. Then let's divide that by 3 times 0.122. Okay, so we have 1379.67. 1379.67. Let me just double check. 1379.67 Rankine. If you are asked to solve for T sub 2, which is in Fahrenheit, then you simply have to subtract 460. And the answer is 919.67 Fahrenheit. Okay? Degree Fahrenheit. So that's the answer for temperature, the final temperature. And then we go with the change in enthalpy. Okay? The change in enthalpy is equal to m C sub P times the quantity T2 minus T1. And from the first discussion, we also have heat is equal to mc sub P times the quantity T2 minus T1. So, therefore, what does this tell us? That your heat and your enthalpy is equal. Okay? So, we have delta H is also equal to the heat, and heat is equal to 300 BTU. So, 300 BTU. So, parang bonus na yun, guys. Okay? Next, we have your work. The work here that we are required to solve is actually the non-flow work. And the non-flow work is equal to the integral of PdV from 1 to 2. Since P is constant, so we only have the integral of PdV from points 1 to 2. So therefore, our formula there would be P times V2 minus quantity V2 minus V1. But we are not given the value for the volume. Instead, we are given the temperature. So what we can do there is derive from our perfect gas law, PV is equal to MRT. So therefore, we have work non-flow. Here you have P2V2, and P2V2 would be equal to MR T sub 2. Your V1 is equal to MR T sub 1. Okay? So your non-flow work would be equal to MR times the change of temperature. Okay? So we have 3 pound mass times 38. We have pound force feet per pound mass Rankine. And then we have T2. Let's just go back. We have 1379. 1379.67 minus 560 as our T1. So again, let's examine the units that can be cancelled. We have here Rankine cancels out, pound mass cancels out, and since this is in pound force feet, therefore we need to divide. We need to divide again 778 pound force feet per 1 BTU. Okay? So this one cancels out and the final unit is in BTU or British Thermal Unit. Let's get our calculators. We have 3 times 38 times the quantity 1379.67 minus 560, and then let's divide that by 778. Okay, so we have 120.11 BTU. Okay, so let's check this one. And then finally, the last unknown would be delta S. Okay, the change in entropy. Now, the change in entropy, one basic formula is equal to Q over T. And we know that Q is equal to MC differential T over T. Since mass and your specific heat is constant, and since this is a isobaric process, so therefore that would be C sub P. So we therefore get the integral of differential T over T, okay, from points 1 to 2. And if we integrate, that will be equal to MCP times the natural logarithm of T2 over T1. Okay, so we have delta S. So again, remember this formula for delta S. We have mass, 3 pounds. For C sub P, let me just check. For C sub P, we have 0.122 BTU per pound mass Rankine. And then we have the natural logarithm of 1379.67 over 560. So we have delta S is equal to, so final unit is BTU per Rankine. So let's do first 1379.67 divided by 560, and we get the logarithm of that, the natural logarithm. Okay, and then we multiply 0.122 times 3. Okay, so what we now have is 0.330 BTU per Rankine. Okay, so check din natin to, delta S. Okay, so class, if you are let's say A, B, C, let's say you are also asked to find, or let us you're also asked to solve for delta U, or the change in internal energy, the formula for delta U is always mcv times T2 minus T1. Okay? So if you are asked to find that, then let's just calculate it. So we have 3 pounds times 0.122, no, 0. RC sub V is equal to, let's solve it from the formula of our K. So we have K is equal to Cp over Cv, and then therefore C sub V would be equal to C sub P over K. Okay, so C sub P is 0.122, and then let's divide K, 1.667. So that would be our C sub V. Okay, so next, delta T. So we have 1379.67 minus 560. So this is in Rankine. This one, the unit of this one is BTU per pound mass Rankine. So in that case, pound mass cancels out, Rankine cancels out, and the final unit is in BTU. So we have delta U is equal to, let's get our calculator. We have 3 times 0.122 times 1379.67 minus 560. Then let's divide that by 1.667. So we have 179.96. Okay? So that is, kung sinama na natin, sinama na natin sa unknown yung delta U. So problem number 2 for our isobaric process review problems, we have, while the pressure remains constant at 689 kilopascal, the volume of a system of air, so take note of this, system of air, okay, changes from 0.567 cubic meter to 0.283 cubic meter. So we see here as well that the volume from V1 to V2 decreases. Okay, so if it decreases, then it means to say that your work would be negative. Okay, because if the volume would decrease, then that means to say the work would be done on the system, okay, not by the system. So let's solve this problem. We have here our unknowns: delta U, delta H, Q, delta S, and also the non-flow work. So let's write P is equal to 689.5 kilopascals, and then you have the volume V1 is equal to 0.567 cubic meter, and V2 is equal to 0.283 cubic meter. Okay, and then I emphasized a while ago that we are dealing with air. So if we are dealing with air, then our C sub V would be equal to 0.718 kilojoule per kilogram Kelvin. Our C sub P would be equal to 1.005 kilojoule per kilogram Kelvin. And then we have K is equal to 1.4, and R would be equal to 0.287 kilojoule per kilogram Kelvin. Okay? So the first thing that we want to solve here is our delta U, and it's equal to mcv T2 minus T1. But we are not given the temperature, so we just have to solve for the temperature using the perfect gas law. You have PV is equal to mRT, then therefore T would be equal to PV over mR. Okay, so if we would substitute that to our delta U, we have mcv, T2 is P times V2 over mR. Remember, pressure is constant, so I don't need to write P sub 2. Then P1, PV1 over mR. Okay? So we could cancel out P, and we could also cancel out from the denominator M times R. So what is left here is V2 minus V1. So that would be our working formula for delta U. Cancel out M. So pressure is equal to 689.5 kilopascals. So kilopascals is kilonewton per square meter. And then C sub V, we have 0.718 kilojoule per kilogram Kelvin. Then the change in volume, 0.283 minus 0.567 cubic meter. And then divide that by your R, which is equal to 0.287 kilojoule per kilogram Kelvin. Okay, so we could cancel out this set of units, also cancel out square meter, and then therefore leaving us with kilonewton meter. Now kilonewton meter is also equal to kilojoule. Okay, so let's get our calculators and let us solve for delta U. We have 689.5 times 0.718 times the quantity 0.283 minus 0.567. Then let's divide that by 0.287. So the answer is negative 489.89. We have delta U 489.89. Delta U is equal to 489.89 kilojoules. Okay, so let's just box our answer. Then we have delta H. Delta H is equal to MCP T2 minus T1. But for the same reason, we don't have T2 minus T1. So similar to our delta U, which is PCV over R times the change in volume, then our delta H would be PC sub P over R multiplied by the change in volume. Okay, so we'll have pressure 689.5. I won't write the units down because I have already shown the cancellation. We have C sub P, which is 1.005, and then we have 0.283 minus 0.567. I would just like to check. Then all over 0.287. So again, let's get our calculators. We have 689.5 times 1.005 times the quantity 0.283 minus 0.567, then divide by 0.287. So we have 685.70, negative 685.70 kilojoules. Okay, so let's box that. So this is already checked. Next, the heat. So as I have discussed with problem number 1, heat is also equal to MCP delta T, and that is equal to your delta H. So therefore, Q is also equal to negative 685.70 kilojoules. Okay? So check na rin to class. Next, we have delta S. So as previously discussed, we have delta S is equal to MCP times the natural logarithm of the ratio of T2 over T1. But again, we don't have T2 over T1. We only have the formula, again, for T from the perfect gas law, which is PV over MR. So if we are to substitute that, then we'll have MCP ln. So again, T is equal to PV over MR. We have PV over MR. So this will be, of course, V sub 2. Then we have P V sub 1 over mR. So P cancels out, M cancels out, R cancels out, and therefore the working formula for our change in entropy is ln V2 over V1. Okay, I hope that is clear. So we have M. We also don't have our mass. So what we will solve here is what we call specific change in entropy. Okay, we will solve delta S over M. Okay, and it's C sub P. C sub P is equal to 1.005 kilojoule per kilogram Kelvin. And then the natural logarithm of 0.283 over 0.567. So we have 0.283 divided by 0.567. Let's get the natural logarithm of that. And we multiply 1.005. So we have negative 0.714 delta S over M, negative 0.714 kilojoule per kilogram Kelvin. So let's box that. Let's check that we have already solved it. And then last is the non-flow work. So the non-flow work is simply equal to P times the change in our volume. So as I have, let me just reiterate that since we have a change in volume which is decreasing, then therefore, of course, we are expecting a non-flow work that is negative. Okay, so we have 689.5. This is kilopascals or kilonewton per square meter. And then we have V sub 2, 0.283 minus 0.567 cubic meter. So again, this cancels out. Final unit, kilonewton meter. So we have 689.5 times a quantity 0.283 minus 0.567. So the answer is negative 195.82. Negative 195.82 kilojoules. Okay, so I hope you have learned something from watching this video regarding isobaric process.